based off of all the information that we've talked about up to this point in the class, right, you can tackle this question one of two different ways. Right? And if you were here earlier, you may have overheard me mention it. I would argue there's an elegant way to go through and do it, right? Which is just looking at relative sizes of numbers, the signs, positives and negatives, and you can extrapolate out what would happen. Right? Or there's the brute force method, which is, I don't really want to think about it, I'm just going to slam numbers into an equation and then make comparisons at the end. Both methods work. Both methods should lead to the same conclusion, right? Because one is a little bit more cerebral, that elegant process. You have to be real careful with your signs and all those, right? It's easy to goof that one, but you should be able to navigate both methods. Right? So spend a minute going through and trying to figure this out. I'll add one more thing. Sorry, I forgot. That delta H and delta S, we should assume at 298. Right? So we want to know what happens when we change the temperature. Note we have a KEQ at 595. If we can figure out what the KEQ is at 298, we can now make a comparison. When we increase the temperature, what happened to that value? Make sense? Then with that, spend a minute to try and figure it out. Start putting stuff together. Okay, in theory, we have both methods up there. I would argue one of them doesn't, well, actually, neither of them fully explain all the way through. But on the left-hand side, we've got what I would call the brute force method. We're taking our delta H or delta S, we plug it into our delta G expression. Okay? For me personally, it was easier to convert the delta S into kilojoules by shifting the decimal point. Okay? So we have to make sure we take that into consideration when navigating this, right? Okay? Assuming the calculation was done correctly by one of your classmates, and if somebody could verify, that would be nice, you should get negative 66.863 kilojoules. You got a verification second on that? Cool. Okay, so we should be getting a negative delta G. If we go through and take a look at the expression on the right, you'll note that I don't say we have a negative delta G. Why not? When we sub in those signs, what are we going to see? A temperature dependence. Okay? So at large temperatures, I would get a positive delta G. At small temperatures, I would get a negative delta G. What do you think 298 is, large or small? Okay, if we're looking at room temperature, that's probably a small temperature. Okay, room temperature usually sits, and small and large are all relative, but that's usually where we would call that a small. Which means internally consistent, I'm saying we should get a negative delta G, and you're getting a negative delta G numerically as well. We can then take that information and sub that back into our expression. Okay, this is where we have to be careful. If we look at the work that I've written, K equals E, that makes sense. We subbed in our delta G. However, that is a negative, which means that needs to become positive. Okay, so my work was bad, and presumably your classmate's work was actually correct. Okay, note we're going to encounter another issue. When we bring in R, what are our units on R? That's an important thing to know, and if you're like, I don't really know that, guess what you should find? Your note sheet right now that you're going to use on the exam, and you should write down R and its units. What are the units on R? Joules per mole Kelvin. Why is that important? If I take directly my delta G that I had in units of kilojoules, it's not going to do a proper unit conversion. Okay, so I had to convert my negative 66 kilojoules into joules so that the joules for my 8.314 would cancel. Make sense? I'm running it at 298 degrees Celsius in this case. This should give me a number, 5.25 times 10 to the 11th. Okay, we've got at least a secondary confirmation on that. So if we're looking at that brute force, okay, what do we need to do? Well, we need to look at our K at 298. Sorry, that's a little cramped down there. Does that work? That doesn't work very well. Can I erase some of the math? some of the math, it's a pretty big chunk of it. Okay, at 298 Kelvin, I've got that K, and what was it, 595? My K is equal to 200. So what happened to K when I increased the temperature? It decreased. Okay, make sense? So we can see that now numerically after running all of those calculations. What's happening on the other end? Okay, so on the other end, I'm going through and recognizing the temperature dependence. Okay, large T means my delta G is positive. If the delta G is positive, I'm reactant favored. If my delta G, if I have a small t, I'm delta G negative product favored. Okay? So K will be larger than 1 if product favored. K will be smaller than 1 if reactant favored. As I increase temperature, I'm going from my reactant, if I increase temperature, I flipped the words. That was obnoxious. You see what I mean by flipped the words? That didn't work at all. So let's erase that. Okay, because I want to maintain the pattern that I've got to help clarify this. So at a large T, I'm reactant favored. If I'm reactant favored, what does that mean about my K? It's not an increase or decrease, it's now the size of it. If I'm reactant favored, I have a K that is less than 1. So you got the right idea, just careful with the increasing, decreasing. If I'm product favored, my K is greater than 1. So now what's happening is I go from a small t to a large T, product to reactant, what's happening to my K? Larger than 1 to becoming smaller than 1, which means when I increase the temperature, what happens? It decreases. What did I see over here? It decreased. Both methods get you the same answer. You're just approaching it from a slightly different viewpoint. Kind of make sense? Okay. The, what I would argue, elegant method hinges on is recognizing this system here. Okay. That system ties back to something that we've talked about a whole lot. Okay. What that talks back to is what I've been referring to as the quadrants. Does that sound familiar? Okay, some people are saying yes, some people are saying no. Before I move on to the quadrants, to make sure you know what I'm talking about, are we good with everything that's written up there? Okay, delete everything. What am I talking about with quadrants? Sorry if you get sick. If you get sick, close your eyes. Where'd it go? Oh, Lord have mercy, come on. That's close enough. This is our quadrants. Okay, that diagram in our lower right-hand corner. Okay, and interestingly enough, we saw it as a full slide, and we're actually going to see it show up on the slides again in a few. I should have actually gone forward, not backwards. Okay, so by recognizing what's happening within those quadrants and what that means to our delta G's, we can then start to manipulate things without actually using numbers. Okay? So it's going to depend on the phrasing of the question. If the question is asking how much does the K change, sorry, you got to quantify it. You're going to have to go through and put in all the numbers to figure out how much the K changed. Okay? If you're just asking, did it increase or decrease, you don't have to plug in all the numbers. You can kind of backtrack your way through it based off of understanding those relationships. Kind of, sort of? Okay. Again, close your eyes. Whoop. Nope. Nope, that was, we already did that. Ah, there's where I want. So that's where we're at. Finally, we're back to it. Yay? Okay. So, new question. Fast, though. How does increasing the temperature affect the rate of a reaction? For those of you preparing for taking an exam 1 retake, this should be an easy, fast question. Speeds it up. Okay? How does it speed it up? Harder question.
It allows the molecules to react with each other at a faster rate.
Why? All you really just said is it speeds up.
Oh.
Okay, increases the number of collisions. If they move around more, I get more collisions. Is that my pen getting capped? Is that my pen getting capped? My pen is still not capped, but that's a hell of a lot more collisions, right? Okay, so yes, I get more collisions, but there's other factors that contribute to it. Okay, does increasing the temperature affect those other factors? So what's one of those other factors? Orientation. Does changing the temperature affect our orientation? Not really. Your particles may move more, but they're now more random, and you're more likely to be out of orientation as you are in orientation. So the orientation isn't really getting affected much by changing the temperature. But what is getting affected? So here we have proper orientation. Did I get a chemical reaction? No, why not? Not enough energy, not enough activation energy to clear it, which means increasing the temperature does increase the number of collisions. Great. But it also provides enough energy to clear the activation barrier. Okay? So that's two aspects that's happening with an increase in temperature. Make sense? That button doesn't work. Okay? So which rate constant increases more when the temperature is increased? Okay? And that can sound a little bit weird, so something that we could do to help with this is that we could start to bring in some of the information that we already know about our rate constants. Okay? And in particular, when we're talking about equilibrium. So what we could do is look at an energy diagram. This is just an example energy diagram, and we'll come back to that in a second. Okay? As I increase the temperature, which of those things is going to be affected more? Okay? So what are we talking about? I've got the activation energy for the forward reaction. I have the activation energy for the reverse. Okay? As I increase temperature, are those rate constants going to be equally affected? It's a hard question. Chew on it a little bit, talk to your table. Which rate constant is going to increase more? What do we think? The reverse rate constant will be affected more. Why? Okay, and this is where we have to be careful. This is all dependent on the graph that we're looking at. If we change the graph, our interpretation could potentially change. So we've got to be real careful processing that. Right now, the forward reaction is running. If I increase the temperature, yeah, it's going to speed it up a little bit, but that activation barrier is relatively small, which means the majority of my particles are already jumping over the line anyway. What about the reverse? Hardly any of them are clearing it because it's such a large activation barrier. So when I increase the temperature, it starts to flatten out, and that's going to put a larger contribution of particles able to clear that activation barrier. Okay? Which means when I change the temperature in this particular scenario, K backwards, or K reverse, depending on how you want to look at rate constant, we should make sure we use rate constant, not K, okay, is going to have a larger change in effect than the forward. Kind of, sort of? Okay. And then this was a slide that stumped me. I was like, I have no idea why this slide was up here yesterday, but now I know. Okay, why is this up here? Okay, what we're talking about, and the slide unfortunately is missing some of the pieces that would have triggered it better, was we're looking at the activation energy. But wait, are we looking at one activation energy? We've got the activation energy for the forward, and we have the activation energy that's a little bit off for our backwards or our reverse. So there should be two activation energies on this diagram. Okay? And if we're considering this, what do we know about the forward activation energy in comparison to the backwards? It's lower. Okay, so let's go ahead and just leverage this and call this the reverse. I need to have another, let's color code that. That's my reverse. I would have a lower activation energy for the forward. If I'm now looking at the number of particles that clear, all of those particles already cleared, we're not seeing as large of an effect as we are with the backwards one because of where those energies are within that. Yeah, you're increasing it, but relative to what was already clearing it isn't the same magnitude. Kind of, sort of? And if you really wanted to, that's where you could bust in calculus, and you could start looking at the calculus curves and the area underneath and integrate all that to prove that ratio. Okay? And if you're like, what the hell, then exactly, don't. Okay? So how do delta G and KEQ change as the temperature increases? Wait, didn't we just solve this? Didn't we just solve this? How would our equilibrium constant, well, this is just talking about the KEQ, change, right? Why are we looking at it again? Take a look at the things that controlled our calculations. The things that controlled the calculations were the delta H and the delta S. Okay? And in particular, the delta H and the delta S for the one we solved was negative and negative. Ooh, they're different. Those delta H and delta S's are now positive. Okay? So what we're trying to do with this, I believe, I haven't had a conversation with Dr. Schneblin, is pointing out that we can't just say the KEQ, I already forgot what our summary was. The KEQ decreased as we increased the temperature. Was that our conclusion? Okay, we can't just make that blanket statement because it's dependent on the chemical reaction. And in particular, dependent on which quadrant you're in within those quadrants. What are the signs on your delta H's and delta S's? Okay, I understand where you're going with that, but it was more a rhetorical question. Okay? That's what we have to consider when we're evaluating this KEQ change. Does that make sense? Okay? In this particular case, are you given a KEQ? No. So how could we go through and brute force this? Plug in two different temperatures. Okay? And what we're going to end up assuming is that our delta H and delta S are relatively constant for those individual temperatures. Okay? Yes, there will be some temperature dependence, but it should be mostly constant. What was delta H a representation of? I know that was fast. So let's slow it, just ignore everything else. What was delta H? What did delta H represent? Enthalpy. What does enthalpy represent? True, but what is you're using more words. What are those words representing? What changed for you to look at a delta H?
Adding or removing heat.
Where did the heat come from? If you lost heat, why did you lose heat? What happened to cause the heat loss? If you had to put heat in, what happened to cause that heat gain into the system? Why was it necessary? What causes enthalpy? I can make it real sick and flip backwards in the slides. Should we do that? Let's see if I can scroll better. We're at slide 66. Let's see, is this going to do what I want? Oh, this will do what I want. Lovely. Do it. Yeah, look at that. Nope, never mind. Okay, it did it on my screen. Now it's going to do it for your screen. What was enthalpy? It was the bond energy. Okay, it was the difference in bond energy. Is the bond energy going to change when you change the temperature? It's the energy required to keep those atoms next to each other. Regardless of the temperature, that's going to be a standard value. Changing the temperature can cause that bond to break because I'm at a higher energy and I can now overcome the bond energy. But the bond energy is relatively constant. We can look at entropy. I'm looking at changes of state. Okay? But changes of state, numbers of particles. Okay? Those were my first approximations. Temperature is important, but it's not really going to change the magnitude that much to a first approximation. Okay? Which is why, what did I say, slide 66? Oh, wow, we jumped way back. It's like slide 2. Okay? Which is why, we can make the assumption that our delta H and delta S won't change enough with temperature to change our understanding of delta G and delta, or not delta, of K. Okay? So to figure this question out, we can go through and use the elegant method. Okay? See how the effects of positive H and positive S manifest into G, how that manifests into K, or we pick a low temperature and we pick a high temperature and we plug and chug the crap out of it. And we run 2 side-by-side calculations. Once those side-by-side calculations are done, I can now compare the magnitude of the Ks. Does that make sense? Okay. Pretty sure I won't like this answer. Do we need to do all of that? There's 2 approaches. There's a plug and chug, and there's the just looking at magnitudes. Okay, so there's 2 approaches. Do we need to do both approaches? No. Do we need to do one approach? Yes. Okay. So I've got a couple people saying, yes, we need at least one approach. Which approach do you want? Thank God. Okay. So we talked through how to do that on the past one, right? Okay, so what I'm going to start to do is I'm going to pause the lecture video as I draw up a bunch of stuff as I try and navigate how I would go through and solve this. You need to be doing the exact same thing. Don't watch me, watch you. Figure out what's going on within your systems to figure out how those things manipulate, how you would address what's happening within those reactions. Does that make sense? Okay, and then for the sake of the recording, when we unpause, it's going to be poof, and everything's going to be there, and we'll try and talk through what I've got written up. We good? 1, 2, 3, go. So I'll note, again, I'm a little nervous now. Now I want to go through and crunch all the numbers. But I think I've got this written correctly. If we go through and start with our delta G, if I'm going to calculate that, that's H minus T delta S. My H is positive. My S was positive. If I simplify that out, I'm just looking at a positive value minus the temperature, which means as my temperature gets big, what happens to my delta G? Okay, it should become negative. Okay? If the delta G is negative, what does that mean? K needs to be greater than 1, which means products are favored. Okay? When temperature is small, what happens? My delta G is going to stay positive. Okay? If my delta G is positive, what does that mean happens to my K? Less than 1, my reactants are favored. If we're looking at an energy diagram, if I'm looking at a large temperature, my reactants are higher in energy than my products. Okay, products are favored. Small temperature, it's the other direction around. Kind of make sense? Now looking at answering the question, as the temperature increases, I'm going from small to large. What happens? The delta G, I'm going from positive to negative, which means what happens to my delta G? It's there. If I go from a positive value to a negative value, what's happening to the delta G? It's getting smaller. What's happening to K? I'm going from, and then this I had a hard time, so I got my 0.1s in here. Okay, so 0.1 is less than 1. 2 is larger than K, or larger than 1, so I'm going from a 0.1 to a 2, which means my number is getting bigger. Is that a bit silly to have to add in numbers like that? Okay, if you say yes, you're being mean. Knock it off. Okay? Sometimes it's challenging, so pick a number that satisfies that system that allows you to do that manipulation. Does that make sense? So what you're trying to track is how the delta G and K are related within those individual quadrants. Kind of make sense? Okay. Oops, again, wrong button. Okay. So what this is now trying to show is what's happening with that energy diagram. Okay. Our relative positions of our reactant to product. That relative position of our reactant to product is temperature dependent, so we would have to be careful with which time we're looking at. Okay. This takes us back to our quadrants. Yay, our quadrants. So how does increasing the temperature affect the equilibrium constant KEQ? Well, it's going to depend which quadrant you're located in, because that's going to change the magnitude of delta G, and that magnitude of delta G is dependent on temperature in certain scenarios. For instance, in our upper right and our lower left. Right? So what might we want to add to this diagram? Instead of just looking at delta G's, okay, and this is what I wanted to do with this, okay, our delta G, come on, pen. Delta G spontaneous means negative. Okay, so these are all our spontaneous kind of systems. Those are all referencing delta G. What do I also want to add into each of these cells? How about what's happening with K? Okay. By incorporating that now K information into these cells, I now have an opportunity to be able to navigate and mix and match without having to do any of those fancy thought games that we just talked through. Right? For the sake of deciding which way it goes, if I had a table that summarized all of this information, all I've got to do is look at that table and be like, that's the answer. Does that make sense? Okay. The one caveat within that is that very typically are you told or asked to repeat just what the answer is? Or do most of your quizzes say, explain? Right? There's almost always an explanation part of it. So you can get to your answer, but now you have to backtrack why it's that answer. Does that make sense? That why is working through the processes that we just went through. Okay? And again, that can be done brute force. I just plug in random numbers, and not random numbers. I plug in my delta H, my delta S. If we're looking at temperature changes, I pick a low temperature and a high temperature. I plug those in and I say, look, see how the numbers change. That's my evidence for why I say it increases or decreases. Or we go through and look at what's happening with those individual energy diagrams. Kind of, sort of? Okay. Which then sets us up with the big reveal. Now we've got a table that summarizes all of this information. Okay? We've got our delta G information kind of above that line. And we've got our K information below that line. And you'll note for some of those Ks, they're temperature dependent. All right? So if we go through and look at this one, the K is greater than 1, that upper left-hand quadrant. K is always greater than 1. Why is it always greater than 1? What was delta G? Delta G was always negative. There is no change to it. It's always going to be negative. Which then means my K has to always show favoring for the products. Right? So if we're going through and now looking at the temperature effects, right, so we have what our K would be, and then we have what's going to happen with the temperature. Well, what's happening with our temperature? When we say K decreases, why is it decreasing? What happened with my temperature? K decreases when what? When, someone said it? Yeah, when the temperature increased. How do you know the temperature increased? Are you just godlike? Top of the slide. This is the summary when the temperature increases. That's why we know the temperature is increasing for all of these cases. Okay? What's going to happen to your K's at those values? Okay, your absolute K value, what it is temperature dependent. So at low temperatures, I'd be greater than 1. At high temperatures, I'd be less than 1. As I increase temperature, what's going to happen? K is going to decrease. Okay? So we've got kind of stages within this. I think I've got shades of blue. Okay? So we have what our K value is, and then we have our temperature dependence underneath. Our K values are temperature dependent. Whoops. Our temperature dependence. Everybody seeing that? So for me personally, I would again try and make sure that I've got this table in my notes, but I also want to be able to delineate when those statements are valid. They aren't just blah. There's reasons behind them. There's actually separations. Kind of, sorta? Yeah, cool. I feel better. Sorry. It's my own personal thing. Don't worry about it. Okay? We've got another big summary dealing with temperature and equilibrium. Okay? This is, again, just a summary. I don't want to read it to you, but you should go back and review it. What we're talking about is the differences. Really what they're talking about here, actually I'll step back a little bit here, is that if we go through and look at this slide, what's happening? When is K decreasing? Is K decreased down here? No, K is decreasing only in the top two cases. In the top two cases, what do they have in common? They have a negative delta H, which would be exothermic. In the bottom two cases, your K increases with an increase in temperature. And what do they have in common? It's an endothermic, or a positive delta H. What is this slide doing? Summarizing that same information, but now putting in energy diagrams so that you can see a little bit more what's going on behind those. Kind of make sense? Okay. Which then means, what should we do? If we look at all the cases where our temperature increases, we should shaft you and make a look at what happens when the temperature decreases. You're welcome. I'm going to interrupt. And starting to work through it, we do have a bunch of numbers there, which means what could we do? You can do a plug and chug. Okay, we're talking about the temperature changing, which means we would also have to pick a temperature that matches what the change was. I mean, actually, you can pick any temperature you want. You just have to make sure you're looking at the directionality of the temperature you're talking about. Does that make sense? So the same deals we talked through. Brute force, plug and chug a whole bunch of different numbers, pick a new temperature, run your calculations, see what happens to, in this case, all we care about is the KEQ, right? Or go elegant through those slides and see if the slides can help you process this. We have to realize that our slides showed us temperature increasing. We're now doing temperature decreasing. Okay, so all the work is there. Ta-da! It's there. And I looked at it and I was like, dude, something's not right. I couldn't figure out what the hell was going on. Okay. Finally dawned on me right as someone was like, shouldn't, and I was like, damn it. If K is less than 1, what should my example number be? And if K is greater than 1, my example number should be larger. Okay, some people are shaking their head like, yeah, I was wondering what you're doing. I hate thermodynamics. What happens to KEQ? It's going from a 0.1 to a 10. It gets larger, okay, or bigger. So if we're looking at our KEQ, we're talking about our KEQ getting larger as we decrease the temperature. Okay, if we went back to the slides, you'd be like, well, but that category says KEQ should get smaller when the temperature increases. Here we're decreasing it. So we have to have our frame of reference nailed down. Does that make sense? Okay. Looking at the rest of the question, it says explain from both a kinetic and thermodynamic standpoint. What standpoint did we just address up here? Is this kinetic or thermodynamic? This is all thermodynamics because what are we looking at? Delta G's and our capital K's. Okay? So if I want to deal with a kinetic argument, what do I have to do? Well, what I'm going to have to do is, number one, delete all this. So are we okay with what's up here? Okay? Almost all of it. I need that information. Okay? If my delta G was positive, if my delta G was negative, okay, and I'm going from a temperature here to here, as I drop that temperature, which one of my states is going to be more affected? Okay, so we look at the blue one. As I drop the temperature, what's going to happen to the success rate of my experiment going forwards? It's going to be unsuccessful. Wasn't it already unsuccessful? Yeah, it has a really high activation barrier. So when I'm looking at that temperature, when I go to this system, I'm going to have a larger change or a larger drop in the product energy, okay, because of where my temperature systems are at. Kinda makes sense? Okay. In that change as we're transitioning from blue to orange. So that drop in temperature is going to have a greater effect on the higher energy species. If we looked at the temperature effect when we increased temperature, which one was more affected? The reactant or the product? Let's look at blue. If we increase the temperature, which one is more affected? Okay? The reactant, because the product was already clearing the activation barrier. So increasing the temperature brings that reactant up higher. Kind of, sort of. So you're changing your focal point when you're dealing with, you're changing your temperatures based off of whichever reaction was slower in that particular scenario. Kind of make sense? Okay. The last part, how does this change the concentration of HCN at equilibrium? Okay. First thing I would do is get out of the language of HCN, because when I think K, what do I think? I think K equals, I don't think K forward, the rate constant forward and rate constant reverse. Okay. You're not wrong, but that's not what I think. Products over reactants. I don't think it's the concentration of HS minus times the concentration of HCN over the concentration of H2S times concentration of CN minus. My focus when I think about K is products over reactants. That's it. Which means if I'm being asked a question, how does the concentration of HCN change? What do I need to do? Get it out of the language of the question and get it into the language that I can solve from. What is HCN? It's a product. Okay? Within our energy diagram, high T to low T, because we were decreasing, what's going to happen to the concentration of product? Am I going to get a lot of product at high temperatures? The rate of the forward reaction is very, very, very slow. The rate of the reverse reaction is very, very, very fast, which means I get a hell of a lot of reactants at low temperature. Or sorry, high temperature. At low temperature, what do I get? Flips, and I get more products. So as I decrease the temperature, what happens to the concentration of my products? Those also increase. We can use the KEQs to help with that, but I deleted all the KEQ information. Okay? So here what we're doing is using the energy diagram to predict those changes. Make sense? Ish? Okay. Okay. All we went through and did was kind of BS'd it, right? It's not BSing. Like, we just dealt with signs and said, what do the magnitude of the signs mean? How does that all translate out? Okay. This statement is now saying, well, you have KEQ at 298. Run it at 275. Do the brute force calculation. Okay, 275 is a lower temperature than 298. What happens to your delta G? What happens to your KEQ? So do the mathematics to prove to yourself the process we just went through works, as long as you understand what greater than and less than are. Sorry. Make sense? Okay. And if you're running that calculation, you can run it, but I'm moving on. Okay. How does increasing the temperature affect the equilibrium constant? Okay, so right away, based off of what we just went through, does changing the temperature affect the equilibrium constant? Yes. Does increasing the temperature mean we increase the equilibrium constant? No. It depends on the scenario. It depends on the reaction we're looking at. It's the balance of the enthalpies and our entropies and how that contributes to our delta G and its dependence on temperature. Make sense? Okay. So what we could then flip this to would be something like this, and saying for this chemical reaction, where we have a delta H that's positive and a delta S that's positive, we could go through and do all the stuff that we just did, right? Okay. And we could figure out what the relationship was with KEQ. Or what we could do is take a look at experimental data. What happened to the KEQ as you increase the temperature? Okay, well, I went from bigger numbers to smaller numbers, right? 30 to 9, isn't that a smaller number? Okay, you're shaking your head. Let's process that. Why? They're negative. Yeah, okay, so we got to be careful with the magnitude of our numbers. This is intentionally or unintentionally set up to trip people. Okay? We can see those numbers and we start to zero in the wrong aspects. Make sure you understand the magnitude of those numbers with powers of 10 relative to your signs. Does that make sense? So negative 30 is a small number. This one is bigger. Okay, well, I mean, technically, this is a small number, but this is a smaller number. Make sense? And when we look at the other table, what happened? Okay. We started with a small number, and it went smaller. Okay. So the direction changed. Why did the direction change? Look at the signs on your delta H's and delta S's. Kind of, sort of? Okay. I think we're doing okay. So it depends on your signs. And in particular, it depends on the sign of the delta H, okay, which is a better summary. Okay, so write out the equilibrium constant for this reaction. If we have 2 molar NO2 and 0.5 molar N2O4, is the reaction at equilibrium? Okay, so run this calculation. This is supposed to be a straightforward, fast calculation, so you should be able to go through and do this. Okay? You already have an answer. No, it's not at equilibrium, because what's the follow-up question? What's going to happen to the reaction to get to equilibrium? Okay? So start putting this together. This should be a fast solve. Okay? Again, we'll do the same pause and ta-da, we know K. Okay? Sort of. Okay? If we go through, what we went through and did is said what K was. Okay? Then we said, well, I've got those concentrations, so let's plug in those concentrations. What I want to call attention to is this equal sign. Okay, and we're going to call attention to that real carefully here in just a second. Okay, and I go through and do all this. What you're seeing here is how I did the math, because I don't have a calculator and had to sort of figure it out. And admittedly, I didn't know what 1/8 was. Someone had to tell me that it was 0.125. Okay, but 1/8, there we go. We got an answer, 0.125. Okay, is that the equilibrium constant? No, which means we're not at equilibrium. Okay, so let's go back to that equal sign. What did we say K was? 217.4. Okay, if those were all equal signs, what I can do is bring this equals all the way over to here and say equals 0.125. Is that a true statement? No. Okay, that is false, so I did something wickedly wrong. Okay, and what I did that was wickedly wrong was that blue equal sign. Okay, those aren't equalities. Okay, we assumed it was an equality, and we started to run the calculation as it was and just hoped for the best. Okay, but it's not technically an equality. Okay, so we'll come back to that again in a second. What's going to happen for the reaction to get to equilibrium? So what did I say my not equality equaled? 0.125. How do I go from 0.125 to become 217? What am I going to have to do? I need more products than reactants. To get a K that's larger than 1, I need more products than I have reactants. I've currently got a massive air quotes K that's less than 1. Okay, so I need more products than reactants. Okay, so we've got an Austin statement. We need to add more products. So what's going to happen to the concentration of the N2O4? It's going to increase. How did it increase? How did the N2O4 go up?
You remove some of the
Okay, and now we've got an interesting limit. English language is going to be a dodgy one on this. We removed some of the NO2.
transfer.
There we go. Okay. For the N2O4 to go up, the NO2 has to react, and so its concentration is going to go down so the N2O4 can go up. And why we have to be careful with the language there is I could get to equilibrium by just saying, well, that's what I started with. Well, I'm going to put in, I don't know the math off the top of my head, I'm going to put in 10 more moles of N2O4. I'm supplying it. I absolutely can, for the record. Yeah, I can experiment. There's a jar, I put more chemicals in it. That's fine. Okay? That's generally not what we're trying to talk about. What we're doing is starting with some unknown condition and saying, how is it going to navigate to getting to equilibrium? Okay, so what is it doing? You remember the chart that I really don't like, that graph? Where we had our concentrations? That says concentration in our reactant goes down and our product goes up. Okay? And within that diagram, what was I talking about? Everything in our conversation talks about this part. Everything we've talked about. Because what's true in that part of my diagram? I'm at equilibrium. What does it mean to be at equilibrium? The rate forward equals the rate reverse. Okay? We're at a constant level. Okay? What we just solved for was not in that red box. And we know that because we didn't get the same value. What did we solve for? We solved for what's out here. We solved for that still transitioning. Okay? And what we're now introducing is kind of an interesting concept. This diagram that we've looked at assumed how much products I had. Let me try and phrase that again. How many products did it assume I started with in this diagram? Zero, which is why my line starts at 0. Okay? And as the course of the reaction goes, it increases. Is that what happened in my question? Do I start with 0 products? No. Okay? So what this question is now actually showing is a slightly new variation on this time versus our concentrations. Okay? Our reactant concentration here started up high, okay? And what we're trying to evaluate is where we're at. Okay? It's starting to drop theoretically, but our product concentration didn't start at 0, it started up somewhere. And it's starting to increase. Okay? Those are going to achieve, that's a bit aggressive to make it go all the way to the bottom, but those are going to achieve our equilibrium, right? Our K. What we're asked to solve for is this line going down and this line going up? That's what we're trying to figure out with this question. How is the reaction attempting to get to the balance? Because here, we just said the product was higher, started higher, and if we had this mixture, it continued to get higher. We proved that by solving to figure out where the relationship was. Could I have drawn this diagram yet another way? How about I start with products up here and my reactants down low? Right? You'd be like, well, I would never start a reaction with products down low. You're right. You would never start a chemical reaction with high concentrations of products. Because when we start a chemical reaction, we're trying to make products. That's humans. We make things. Why would we see a scenario where we had a high concentration of products and a low concentration of reactants? Because it wasn't us that made it. Dude, aliens? No. Fucking biology. Okay? What's happening in your body? What's happening in plants? Those are individual chemical reactions. And if we go through to study those chemical reactions, they're going to be a state of flux where our product and reactant concentrations are going to be changing. They're going to be changing according to the laws of thermodynamics and dealing with equilibrium and rates and all that fun stuff. So what we're trying to talk about is now in these new systems, where do we start? Would we predict that chemical reaction to make products? Or is it starting in an equilibrium where it's not doing anything? So we're now changing our perspective. Instead of, I just want to make things, it's now I'm going to study things. Okay? Do you think the biological systems are really straightforward and simple? Okay, really straightforward and simple. That's why you start all courses by zooming in and looking at the sequence of amino acids within a protein. Have you done that? Okay. Some people are like, yes, I really doubt it, even in your bio class. Okay. What they showed you was pretty pictures and said, this was a protein. Ta-da! Okay. When you actually advance enough through the background, now they'll start saying, these are the individual amino acids. These are the hydrogen bonding interactions that's happening within those systems. Because those are very large, complex systems. So if we're going to start to talk about a way to monitor those systems, we don't want to be looking at complex, we want to look at simple reactions. We want to look at reactions that you've been looking at through all of Gen Chem. Okay? That equality, okay, I know I erased it, but I had that blue equal sign, right? You remember that? And I had K over here, and then I had a bunch of red numbers, yada, 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 0.125, the 217. That equality is what we're kind of interested in. We're interested in what's happening out here and how we go from there to here. So we're talking about that transition point. What we decide to call that new thing in red is not K, because we're not at equilibrium. Our systems are still changing. And because it's not K, we can't call it K. We have to call it something else. What do we call it? Q. Q for quotient. Another way of referencing a ratio. What was K? A ratio of products over reactants. Okay? So this next part is now just saying a reaction quotient. We go through and we look at a reaction and we say, what would it be? If I assumed it was K, how would I calculate it? I would calculate it to be 0.125. Okay? The actual K value is 217. What do I have to do to transition from 0.125 to 217? I need less reactants and more products. I can now use that information to help me decide how my reaction is going to change to get to equilibrium. Okay? So if we looked at a new expression, right, the equilibrium expression for this reaction, okay, I know it's blue, tough. You just get to hear me rant. Concentration of CO2 over H2, concentration of our carbon monoxide, H2O. Okay, they were all coefficients of 1, assuming that they were given to you as balanced. Our CO was 0.01. Our H2O was 0.02. Why can we include the H2O this time? Didn't we delete H2O from our expressions? We deleted H2O from our expressions when it was a liquid. It's gas in this state. That's why we're keeping it here. Our H2, 0.3. Thought I saw a calculator in someone's hand. Oh, well. Okay. We're setting this up, okay, in this expression. Okay. The K and Q are both solved the same way. Okay. And if we color-coded it, what we just did was plugged in all of those numbers to get my Q. And now what I'm asking is this true? Is that equality valid? Okay, so 0.4 times 0.3, did you calculate it all for me already? 600. What was the KEQ supposed to be? It's given to us in the question, 21. Are those numbers the same? No. So what does that mean has to happen? The reaction has to change its properties so that I can achieve the equilibrium. All my reactions are going to strive to get to equilibrium. So to get 600 to become 20, what has to change? Well, how did I get 600? It's products over reactants. I need my number to get smaller. What has to happen to the concentration of products? They have to decrease. How did the products decrease? By turning into reactants. So the reactant concentrations will go up, the product concentrations will go down. Whoops. This is the number line that she's trying to establish. Right? All products to the far right, all reactants to the far left. They're equal, K equals 1. When they're equal, how do I go from 600 to 21? I need less products because I'm moving away from the product side. And since I'm moving towards the reactant side, I need more reactants. That's all this is trying to go through and establish. Okay? What this boils into, and I know we're right there at the line, that's the reaction quotient, we'll come back to that, is this fancy description of Le Chatelier's principle. Okay? And it's officially, if its system is at equilibrium, is stressed. Right? So if you see a friend standing balancing on one leg, and you see them balancing, they're a little shaky, what do? You push them. Okay, exactly. Okay? And whichever direction you push them, depending on how nice you are, okay, you're not trying to throw them to the ground, but you are trying to knock them off balance, so they counteract. Okay? So if you push them hard to the left, what do they have to do? Swing back to the right. Left and right, kind of like reactants and products. Okay? Except the push in chemical reactions is changing those concentrations of reactants and products. So anything that affects our reactants and products will change our equilibrium. Right? That's Le Chatelier's principle. What we just walked through technically wasn't Le Chatelier because we weren't at equilibrium. But what is our reaction going to try and do? Get to equilibrium. So Le Chatelier just said, once I'm here, I know it's always going to get back to it. All we've been studying is let's get to it. Right? Does that kind of make sense? Right. With that, I think you actually have enough context to be able to answer all the quiz questions. Okay? And hopefully, Alex, I don't know, we'll see. We'll still talk through some examples of this on Monday. Right? I would encourage you to potentially watch the lecture for Thursday to kind of get in front of it so that you can move, be a little bit more prepared, and be focusing on studying for the quiz next Wednesday. Make sense? Good job. Thanks for bearing with me.